Yeah, let's start moving on to the next talk. Glaucia Murta from the university, the Heinrich-Heine-Unversitat in Dusseldorf. And she will be talking about bounds-only information available to eavesdroppers in a multipartite device-independent scenario. That's a lot of words. Great. Looking forward to this. Thanks.
Okay. Thank you, Friederike. And also thank you all the organizers for putting together this online conference. So I completely agree with what Vadim said. It has been a very nice experience, including the social events that the conference has. Okay, so today I'll be talking, sorry, can you see my video? Great. So today I'll be talking about a work that we have recently developed here in Dusseldorf, and it's in collaboration with Federico Grasselli, Hermann Kampermann, and Dagmar Bröss. And it appeared on arXiv today, so just in time for BQIT. And okay, so as Federica had mentioned, I chose maybe a very obscure title, so I want to clarify that my talk is about quantum cryptography, and in particularly about device-independent cryptography. And I will be also focused on scenarios that involve many parties. So this is what the result I want to tell you about today. Okay, so I will first motivate why do we want device-independent cryptography, and then I will talk a little bit about security proofs. So I have a warning, I'm a theorist, so I will be talking about cryptography from the theory side. So what can we do from this side to get better protocols? And then I will finally present our results that concerns bounds on Eve's uncertainty in this multipartite scenario. Okay, so the BB8.4 for quantum key distribution has been already mentioned in several talks along this week, and it's maybe the standard example to show like the potential of when we bring quantum systems to the performance of cryptographic tasks. So this protocol, it has the nice feature that it achieves information theoretical security, which as opposed to classical cryptography that is based on computational assumptions. Also, this protocol has been studied a lot, and from the theory side, and security proofs have been shown about it, and it can tolerate a lot of noise. So here, noise in QKD is usually measured in terms of the Q-bar. So it's the percentage of mismatch of the bits of Alice and Bob. And also over the past years, there has been a lot of implementations that achieves higher and higher rates, and also longer and longer distance, to the point that even intercontinental communication has been already established. Okay, but the problem of the BB8.4 protocol is that in theory, we have all these advantages, but it requires that for example, Alice prepares a state in one of two bases, and Bob makes measurement in one of two bases. But what they have in the lab are several components, and they need to be sure somehow that they are really implementing what in theory is required for this protocol. But this is very hard to achieve in practice, and this has led to the hacking of many of the quantum crypto systems. So Vadim Makarov has talked about several hacking mechanisms that can be used to attack these protocols. So, okay, so device-independent cryptography is a way to address this problem because actually we want to relax the need of all this precise characterization about the system. So basically what we are going to do is we are going to treat Alice and Bob's labs as black boxes where we don't care about what are the details of this implementation. And the only thing that matters is how many different settings Alice is measuring and how many different settings Bob is measuring, and what are the outputs. So basically we will have like a joint probability distribution of these outcomes given the inputs, and we want to prove security of protocols based on these statistics. And maybe more specifically, we want to look at the violation of a Bell inequality. We want to check that this statistics is violating a Bell inequality. Okay, so to perform a security analysis of protocols in the device-independent scenario is quite a challenging task, because we really relaxed all the characterization that we could have about the system. And there has been over the years many attempts to really establish security. And then finally, we had the entropy accumulation theorem that allowed to establish security of device-independent protocols in the most general type of scenario, where the eavesdropper could even be doing coherent attacks. So with the entropy accumulation theorem, we could establish a security proof of, so here I'm giving two types of protocols. So for example, a quantum key distribution, where two distant parts want to establish a common key. And also another type of protocol that can also be proven secure using these techniques is randomness expansion, where basically Alice and Bob wants to start with a small string of bits that's random, and they want to produce a longer string of random bits. For this case, maybe we can consider the scenario where they are located in the same lab, so their devices are isolated, but they don't need to be separated. So for this task, we are not interested in separation. So in fact, the entropy accumulation theorem established, it's like a much more subtle result, because it also talks about what is the rates that we can achieve in these protocols in the finite size regime. So it takes into account all the finite size effects. But here in this talk, I will be interested about the asymptotic case, which then we can say that for these protocols, if we want to analyze security, we basically need to determine some of these entropic quantities. So these entropic quantities, these conditional von Neumann entropies, basically they give us information of what is the uncertainty that an eavesdropper has about what is Alice's outcome, or maybe here the joint outcome of Alice and Bob. Okay, so basically now the challenging that we have, or the challenging that I want to address here, is that we want to estimate the eavesdropper uncertainty, so basically these entropic quantities in a device-independent scenario. So if I would know what is the quantum state shared between Alice and Eve, I can simply compute this quantity directly. The problem is that in the device-independent scenario, we are making no assumptions of what is the underlying system, or what is how the devices are working. Okay, so in general, if we have the statistics of inputs and outputs, we actually can estimate another entropic quantity that is called the conditional mean entropy. And it has been shown that in a device-independent scenario, this can be done actually by a numerical procedure where we can run a semi-definite programming based on the NPA hierarchy. But the important thing I want to say about that is that we can calculate this quantity, and it's always a lower bound on the von Neumann entropy. The problem is that this lower bound, usually it can be very bad. So it can be the case that the mean entropy is much smaller than the von Neumann entropy. And we know that, for example, if we consider the CH-SCH inequality, that is the simplest Bell inequality for two parties. So here in this graph, I'm illustrating that actually, if we look at the von Neumann entropy and comparing to the mean entropy as a function of the violation, the von Neumann entropy is higher than the mean entropy for all the points except for the extremal points. And this has an effect on the security proof that we can do on this protocol. So on the left side here, I'm mentioning that if we consider the IQKD protocol, so a device-independent quantum key distribution protocol that uses the CH-SH inequality, if we and for the CH-SH inequality in particular, we know tight bounds for both of these entropies, for the von Neumann entropy and for the mean entropy. And if we use these bounds to see what is the noise tolerance of this protocol, so actually we see that if we use the tight bound on the von Neumann entropy, we can, like from the theory side, ensure that we can tolerate 7.1% of Q-bar while if we didn't have access to this entropy and we had to rely on the mean entropy, we could only prove security up to 5.2%. And I mean, this may seem small improvement, but actually current experimental implementations that are based on heralded entanglement, for example, they have this, the amount of noise that the system has is of this order of magnitude. So this can really, like an improvement in the QBER that we can tolerate can really make an experiment available or not. Okay, so I hope I managed to motivate that if we have better bounds on these entropic quantities on the eavesdropper's uncertainty, this can lead to protocol with better performances. Okay, so finally, sorry. Okay, so finally, I'm ready to talk about our results. So in this work, our motivation was, okay, so if bounding the eavesdropper uncertainty is such an important thing, can we do that for other scenarios other than the CH-SCH, for example, that is the simplest Bell scenario? And in particular, we addressed the multipartite scenario. So just to give an idea, if we are now have more than two parties, so we have Alice, Bob, and Charlie, or maybe even more parties, we can think, for example, of new protocols. One of them is the generalization of QKD. So now Alice wants to establish a secret string of bits with both Bob and Charlie, so that she can communicate securely with both of them at the same time. I think nowadays the motivation for this protocol is quite clear, and this is called conference key agreement. In the same way, for randomness expansion, we can also explore these multipartite correlations and think of protocols where we want to use them to establish longer strings of random bits. Okay, so now that we are in the multipartite scenario, then we will have a joint probability distribution of all the parties, and we want our security to be based on the violation of a multipartite Bell inequality. So in our work, we consider the MABK Bell inequality. So here I will not go into details on what this inequality is, but I just want to talk a bit about some properties of this inequality. So this is an inequality where each of the parties has two inputs and two outputs, and it has some interesting bounds. So we can talk about what is the classical bound, so what can be achieved with local hidden variables. We have the quantum bound, that is the maximum that can be achieved with a quantum strategy. And between this bound, we also have what is called a GME threshold. And GME here stands for genuine multipartite entanglement. And this means that if we violate the inequality above this amount, we can be sure that we have a genuine multipartite entangled state that is being used by the parties. Okay, so finally, I can state what was our results. So we managed to prove two results regarding this scenario. So the first one is that we can restrict the analysis. So if we are talking about many parties, they are testing for the MABK Bell inequality, and I want to know what is the uncertainty of the eavesdropper, we can actually restrict the analysis to qubit states. So as I said before, in the device-independent scenario, we don't assume a dimension or anything about the state, but here we showed that we can actually only consider n-qubit states that are almost GHZ diagonal. I will say a little bit more about what almost GHZ diagonal means in a bit. And the second result, we also showed that an upper bound on what is the maximum violation for this inequality that a given n-qubit state can achieve. So if you are a bit familiar with no-locality literature, you might have seen that the second result extends quite old result from the Horodetskys about the CH-SH scenario, so about the maximum violation of the CH-SH inequality. And this first result is a generalization of a result also about the CHSH inequalities that allowed for that tight bound that I mentioned before. So we managed to generalize this result for a scenario of n parties. And okay, so now what do I mean by almost GHZ diagonal state? So here I'm giving an example of 3 parties. And if we write our state in a GHZ basis, which is a basis formed by GHZ-like states, so basically we get a state that is almost, it's basically diagonal except for a single off-diagonal parameter. And if we have any part, is actually this result extends in the following way. So first of all, we can reduce the analysis to make like 2 blocks of size 2. And then out of these blocks of size 2, we can still make some of them to be 0. So actually, when we go for any parties, the number of blocks of size 2 increases exponentially with the number of parties. And we can take a linear number of these blocks to be completely diagonal. So that's what we mean by almost GHZ diagonal state. And the second result is that about the maximum violation of the MAP-K inequality. So we managed to establish that given an n-qubit state, then we can calculate what is called this correlation matrix, which is basically a matrix that represents expected values of Pauli operators in this state. So here I'm just writing down what is it for the case of 3 parties. And then we look at what are the largest eigenvalues of this matrix that is composed by the correlation matrix. And we also show that actually some families of states can achieve this bound. So this bound is tight for certain families of multipartite states. Okay, so finally, we want to use these results to actually, our goal was to bound the uncertainty of the eavesdropper about the party's outcome. So with that, the first bound we had was to prove a tight bound on the entropy of the eavesdropper about Alice's outcome. So here I'm talking about 3 parties. And now I want to comment a bit about, so this plot is showing the bound, and I want to comment a little bit about the consequence of this plot. So actually, we realized that the bounds that we derived, and we managed to prove that it's tight, it coincides with a bound that was derived previously, actually in our work that I did together with other authors. That is based on a relation of the MAP-K inequality with the CHSH inequality. So it was a completely different approach, and we didn't know if this bound was actually tight. So now we managed to establish that actually, yes, that bound was tight. And then we managed to show that actually the bound is tight for any number of parties because we can exhibit a family of states that attains the bound. Another thing that we can observe here, so the MAP-K violation, so if it's above 2, I'm having a violation, and here I'm showing what is the GME threshold that I mentioned before, that can only be violated if your state is a genuine multipartite entangled. So we can see that actually we can only has uncertainty if the violation is above the GME threshold. So this graph is for 3 parties, but actually this statement holds for any number of parties. And then maybe a more negative result is that unfortunately we can conclude that the MAP-K inequality is not useful for device-independent conference key agreement protocols. So this fact, it has been discussed before based on the bounds that existed about the MAP-K and CHSH correspondence. And then the fact that this bound is tight, it means we cannot do any better. So unfortunately, this inequality is not useful for this protocol. And the point is, even though we have some positive entropy here for conference key agreement protocol, so since we want that all the parts share the same key, they need to communicate some information to correct for this key. And then unfortunately, this second term here completely kills all the entropy, all the uncertainty that the eavesdropper has. Okay, the second bound that we obtained was a bound on the joint outcomes of Alice and Bob, given the Eve's information. And this is showing the green curve here. And for this case, we can see that we actually have a positive entropy for any violation of the MAPK Baire inequality, so not only above the GME threshold. And here we are comparing, so actually this pink curve here is a tight bound on the mean entropy that was derived in a previous work. And then we can see that with our approach to try to get analytical bounds directly on the von Neumann entropy, we get like a significant improvement. So for this case, we can see the same situation, that the mean entropy is indeed a bad bound for the von Neumann entropy. And I just want to mention that this improvement can really impact rates of randomness expansion protocol. So it can really lead to higher rates. Okay, so finally, before I conclude, so maybe the take-home message that I wanted to give here is that one way that we can improve protocols is by having better bounds on Eve's uncertainty. So this can lead to protocols with better performances. So we have derived like two results that significantly simplify the analysis of device-independent protocols in these scenarios, and then with that we could derive bounds on the Eve's uncertainty for the case when the MAPK inequality is tested. So to look further, like as future work, so actually I mentioned that the MAPK is not suitable for conference key agreement, but recently there has been a family of inequalities that was proposed, and these inequalities, they really reproduce all the nice properties that we want from a conference key agreement protocol. So it would be very interesting to extend these results to this type of inequalities. The point is that these inequalities are not so symmetric as the MAPK inequalities. Finally, we can, like this analytical approach, it opens the possibility of trying to calculate Eve's uncertainty regarding other parts outcomes, and but then like to really analyze whether this is gives good results for example, randomness expansion protocol, then a more careful analysis has to be performed. And lastly, I want to mention that the MAPK has been used to another cryptographic task that is called secret sharing. So there has been attempts to make device-independent secret sharing protocols using the MAPK. So far, they were unsuccessful. And more recently, there has been a different approach using more general causal structures. So not only based on Baire inequalities, but more general inequalities, which seems promising, but still it's missing a formal security proof. Okay, so with that, I thank you for your attention.
Great, thank you very much, Glaucia. It was great to have a talk like this in between all the experimental talks. We often forget how much theoretical work there's behind all the stuff that we do. There are already a few questions who have come in. Francesco Graffiti asks, have you considered, sorry, it keeps jumping around. Have you considered the experimental feasibility of almost GHS diagonal state sources?
Very little from my side. You mean like if they can be implemented, or, but I, like lately I've seen some works approaching preparing GHZ states. I wouldn't know how to comment in details of what is the state of the art from the experimental side, but there has been some effort on that. Okay. For sure, Baire states are easier to prepare than GHZ states, but yeah, so this is maybe looking ahead in the future.
Great. Another question from Francesco. Communication aside, does MACB violation give us some knowledge on the underlying world as well on local hidden variable theories, or Svet Lichny on multiparty local realism?
Sorry, can you repeat a bit slower?
Communication aside, does the MABK violation give us some knowledge on the underlying world?
Okay, yes, so this is standard Bare inequality is actually a facet of the set of local correlations. So if we are violating, it also means that there is no local hidden variable models behind that. Maybe this inequality has interesting property. It also reflects the sometimes called GZ paradox. So for odd number of parts, we really achieve the how can I say that the maximum algebraic bound of the inequality. So it is a standard Bare inequality.
Okay, great. I think so. Could you maybe explain briefly what this GME threshold, how it's different from a quantum threshold? What's the theory behind that?
Okay, so the quantum. Okay, when we wait, I wanted to go here. Yes. So a quantum threshold is the threshold of everything we can do with a quantum strategy. But when we have multipartite entangled states, then we have different types of entanglement. So for example, we could have a state where I have entanglement only between Alice and Bob and not with Charlie. Mm-hmm. So, and maybe these states, which are not genuine multipartite entangled, they can already violate the inequality, but not as much as this threshold. So the thing of this threshold, it can really guarantee, and you can see it as a device-independent certification of genuine multipartite entanglement.
Okay, great, thanks. That was really clear.